So last chapter was on gases, and this chapter we begin solids and liquids. This is, again, almost entirely review. You had this stuff in physical science, you're having it now, and then it will come back and say hi to you again in physics. So it's, yeah, and you probably talked about the difference between solids, liquids, and gases. It's all about third grade. So lots of this stuff should be new to you. There's going to be some new detail that you haven't had before, but the concepts should all just be already there in your brain, and you go, oh yeah, that makes sense, as you add a little more detail to it. So solids and liquids. We're going to talk about first intermolecular forces. The reason that solids and liquids are not gases is because they are being held together tighter. And so we need to look at the forces that hold molecules to each other. Forces that cause one molecule to interact with another are called intermolecular forces. That should make sense. Molecule to molecule intermolecular forces. There are several kinds of them. There are dipole-dipole forces, and I'll show you a picture in a minute. Dipole-dipole are partially positive parts of one molecule that attract to partially negative parts of another molecule. So any polar molecule where there is a part of the molecule that's slightly positive that we would have labeled a couple of chapters ago as delta plus will be attracted to any part of another molecule that is partially negative that we would have labeled delta negative. And so positives and negatives attract one another. And so if I'm a molecule and I've got a positive part and a negative part, and there's another molecule out there that has a positive part and a negative part, my positive part will be attracted to that molecule's negative part, or vice versa. Its negative part will be attracted to my positive part. And so those will hold molecules together. And the stronger those molecules are attracted to each other, the stronger the dipoles of those molecules, then the more cohesive that substance will be. So strong dipole-dipole forces will exist between things that are a solid at room temperature, because they really are attracted to each other. And so even though we're giving it a fair amount of thermal energy by letting them be around at room temperature, they're still solids because they're attracted to each other, and their thermal energy is not enough to overcome the attraction between the dipoles. Things that are less strongly attracted to each other because of these kinds of interactions would be liquids at room temperature. The thermal energy has allowed them to move around and slip past each other. They're still attracted enough to each other that they're not gases, but they're not as attracted to each other as solids are. Okay, so dipole-dipole forces is one intermolecular force. Another one is a hydrogen bond. This is a particular kind of dipole attraction. Hydrogen bonds are different than hydrogen bombs, obviously. A hydrogen bond is when you have an oxygen-hydrogen pair, and the oxygen pulls almost all of the electron presence away from the lone proton sitting out there as the hydrogen atom. And so it's a very polar bond. And basically you wind up with an oxygen-rich region around the oxygen and a lone, lonely proton sitting out there wishing it could play with its electron rings, right? And so that's a very strong kind of dipole, and they are fairly frequent, especially in organic chemistry where you see oxygen-hydrogen pairs. And so those oxygen-hydrogen pairs form a dipole, and molecules that have oxygen-hydrogen bonds are strongly attracted to each other because of dipole interactions, okay? And this greatly influences solubility. The hydrogen bonds like to be next to each other. The proton of one is attracted to the oxygen-rich oxygen of another, and so these two molecules will attract each other at the regions of hydrogen bonds. And they will mix with anything else that is polar, that has positive and negative charges. But they don't very much like to be separated by things that are not polar. They don't want to dissolve non-polar substances because they like to be close to each other, and if a non-polar thing gets in there, then they don't get to hang out next to their friend as much. And so they reject that. And substances that are not polar don't dissolve very well in polar substances. Okay, and we'll play with that a little bit with some labs in a little while. So here is just some pictures to show you dipole-dipole interactions, right? Partially negative, partially positive, and the partially positive regions will attract partially negative regions and will repel partially positive regions. So the molecules tend to orient themselves positive to negative and negative to positive, and they like to hang out with each other because all of that electronegativity or attractive forces make the substance hang on to itself. And so the attractions are able to overcome thermal energy. Just another picture, this molecule that has 3 chlorines around a carbon and 1 hydrogen. The hydrogen, poor sucker, loses out big time with the electronegativity. So this region becomes very electronegative, this region becomes very electropositive, and they like to orient themselves negative to positive. And so that compound would be very cohesive. That would be a solid or a liquid at room temperature. It would not be a gas because it likes to hang on to itself. Okay, thermal energy has to build up before it starts to spread out. Here's another one. This is a dipole-dipole that's particularly a hydrogen bond. So water molecules, the hydrogen loses its electron to oxygen, and it is a covalent bond. It's not an ionic bond, but the electron is almost never around the hydrogen. So it shares its electrons very heavily towards the oxygen. It becomes a sad little proton hanging out here. And he is attracted to the negative region of this water molecule. And so water tends to, again, hang out with itself. You've got to add a lot of energy to it before it starts to spread out and become a gas. Okay? Another intermolecular force is called a dispersion force or a London force, described as the forces that exist between non-polar molecules as a consequence of random electron positions, which is a temporary dipole. So in a normal dipole, in a normal polar molecule, the electrons are always hanging out around this particular atom. And they're almost never hanging out around this other atom, which creates the partial negative, partial positive relationship and causes the dipole interaction. Well, even in non-polar molecules, where everything is shared equally, because electrons are zipping around and they are being shared, there will be split-second moments in time when a molecule has more electrons in one part than on another. We could illustrate this if we wanted to, if we were to say that all of you are electrons and your desks are the protons, the nucleus parts of the atoms. And if I were to tell you to get up and run around the room and stay next to a desk, but not necessarily your own, you would all be shared equally amongst the desks, but there would be moments when nobody would be standing at a desk, or there might be 2 people standing at a desk, because you're all just running around chaotically around the room. You're all being equally shared, but there are moments in time when there's more electrons somewhere than somewhere else. And so a molecule that has that situation will be just for a second a dipole. And maybe another molecule next to it is just for a second a dipole as well. And so they'll attract each other, they'll be like, oh, okay, just kidding, I'm not a dipole anymore. And those little momentary interactions that are not permanent is called a dispersion force because it has to do with where the electrons are dispersed on the molecule. The electrons may be for a moment towards this end and not the other one, so that becomes temporarily positive and the first one becomes temporarily negative, and then it'll orient itself next to somebody else that is like that, and then it'll say, oh, just kidding, that's over. We wound up not being attracted to each other. And so these forces are temporary and they're very small. It's much, much weaker than a real dipole, which means that molecules that are only attracted to each other because of London forces or dispersion forces tend to be gases at room temperature or gases at just above room temperature because they don't really, they're not holding on to each other. These intermolecular forces are not very strong. So you add just a little bit of thermal energy, and it's like, okay, yeah, never mind, peace out, I'm out of here, bye-bye. And it becomes a gas, right? And so much weaker than real dipoles. The bigger the molecule, the more likely it is to have London forces. If it's only a small molecule, then if electrons are over here, they're going to so quickly go back over here that it doesn't have time to build up. But if you've got a really long molecule, you can have a moment where all the electrons are over here, and we get a good strong dipole for a moment or two before the electrons all migrate back down the other end. So bigger molecules tend to have this more than smaller molecules. This is why nonpolar substances have much lower melting points and much lower boiling points. Okay, nonpolar substances like gasoline. Gasoline is nonpolar. Okay, and at what temperature does gasoline boil? Anybody know? The answer is just a little bit above the temperature of our normal life living. If you take gasoline and you set it in a cup and you put it in the sun, it'll very quickly turn into gas. And it won't like boil, you won't see the boiling aspect of it, but it'll evaporate really quickly because it just takes a little bit of solar energy to turn it from a liquid into a gas. Butane, propane, things like that, they're in a liquid form when it's compressed into a cylinder, and you buy a propane cylinder or you buy a butane can. But as soon as you take the pressure off of it, it goes whoo, and it turns into a gas, which is why you can burn it. Okay, and so nonpolars have a very low melting or boiling point because they don't really want to be next to each other. They're only sort of attracted to each other, and only by these little London dispersion forces. Okay, so small molecules have even weaker London forces. Big molecules have larger London forces, and this is the weakest of the intermolecular attractions. A picture real quick just to help you see this. If we have a London dispersion force, we can have it on an individual atom too, where as the electrons are orbiting this neon atom, they happen to be more of them on this side. And if this one were to be having the same sort of experience where the electrons orbiting this neon atom were to be more on this side for just a moment, then this region is sort of positive and this region is sort of negative, and they'll attract each other. But as soon as the electrons spread back out, that attraction force is gone. Okay. And so uneven distribution of electrons in a helium atom could cause a momentary dipole, and then that could even induce a dipole on a neighboring helium atom, which would make them attract each other. But as soon as one of them cancels out, the other one will cancel out too, and that attraction is over. So we started the conversation saying this is about solids and liquids, and then we jumped into intermolecular forces. So now we have a foundation of intermolecular forces. Let's go back and look at the two states of matter we're going to be talking about solids and liquids. A solid is a material which at a given temperature has a strong enough intermolecular attraction that its molecules stay in contact despite the vibration caused by its thermal energy. So that's a lot of words, but you can picture this now understanding intermolecular forces. You have a molecule and another molecule, and they both have thermal energy, they have temperature, and so they're shaking, right? But if they like each other enough, then as they're shaking, they're going to stay in contact as they shake, right? Or they're going to shake like this, where they like to be next to each other, and they're going to stay in contact even though they're shaking. And so a solid, the intermolecular forces are strong enough to overcome the thermal energy. If the intermolecular forces were not that strong, then their shaking would drive them apart, and they would wind up shaking somewhere else. Okay? So the intermolecular forces are stronger than the separation of the vibration that wants to happen because of the thermal energy. Solids have a low diffusion. So if I set a lump of something on the table and I come back tomorrow, that lump of something will still be there because it doesn't vibrate itself away and travel. A lump of sugar stays a lump of sugar in your pantry And if you come back tomorrow or next week or in a year, that lump of sugar will still be there because it has not diffused out into the environment, okay? So they have very low diffusion. They are not permeable. I can't set a lump of sugar on the table and expect that tomorrow it will be under the table. It doesn't like ooze through the table and fall down, right? And so permeability is not something that solids can do. Solids are shaking, they have thermal energy, but they're vibrating next to each other and they don't go anywhere and they don't spread out enough to go through holes of other stuff, okay? So they're not permeable. They have a defined shape and volume. A sugar cube is a cube, and if I put it in a round dish, it will still be a cube because that's the shape it is, okay? This mouse is a solid, and even though it's sitting on a flat surface, it doesn't like ooze and spread out. It still is the shape that it is because it has a defined shape and it has a defined volume. I could take the mouse from the little plastic packaging that it was in when we bought it and then expose it to the room, and the mouse does not go and spread out to fill the room, right? No, it's a solid. It has a defined volume. I can take it outside and put it on the ground, and it doesn't try to fill the atmosphere, right? It's a solid. Solids, solid. They have a defined shape, they have a defined volume, and that is because the intermolecular attractions are stronger than any other state of matter. Okay, does that make sense? Cool beans. So they're moving, but the vibrations caused by the heat are not enough to drive them apart. Okay? Now, we have a couple of kinds of solids, and this is new to you. We didn't get this in physical science. Okay? So, crystalline versus amorphous solids. A crystal solid is one where at the molecular level, if you look at how the molecules arrange themselves with each other, there is a structure. There's a regular three-dimensional arrangement of molecules. Okay? And you could look at it under a microscope and it would have a certain shape. And then as that shape gets bigger, it keeps the same shape, which is why a diamond looks like a diamond, whether it's 100 pounds, which would be ridiculously valuable, or, you know, a tenth of a carat. It looks the same because the arrangement of the molecules is regular and predictable. And so you scale up a diamond and it just scales up that shape. And the shape doesn't change. The opposite of this would be a solid where the relationships between the molecules of the solid do not have a regular predictable shape. And so they just kind of stick together however they want to. They're still a solid, so they're still close to one another, but it's not a predictable arrangement, okay? And so that we call amorphous. Morphe is the Greek word that means form or structure. A means not, so this is without a structure. If we analyze it at the molecular level, it's just chaos, okay? So picture this. Picture a group of students and they're moshing, okay? I know you guys have never moshed because you don't go to those kind of parties. But let's say that you did, right? You're all in a mosh pit and you're close to one another and you're all moving, but you're not moving very far. Nobody is leaving the mosh pit, right? Bang, 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 and you're all crazy. And that's an amorphous solid, right? Vibration, collisions, but everybody's close to each other and there is no structure. That's an amorphous solid, okay? Compare that to the same group of students that happen to also be on a cheerleading squad, okay? And then the next day, there's a football game, and they all make themselves into a pyramid of people. And now they're moving, yay, go team, but they're all standing in this pyramid, right? They're still in contact, there's still motion, but now there's order. Now they're organized into this shape. That's a crystalline solid, okay? So common examples of crystalline solids would be like salt or sugar. salt and sugar crystallize, and they form a regular repeatable structure. Examples of amorphous solids would be like glass. If you looked at glass, the glass molecules, the silicon oxide molecules, are just randomly stuck there next to each other, and there's no structure to it at all. Which is why if you take a crystalline structure and you whack it with a hammer, it breaks along nice clean lines and you get straight edge pieces because the faces of the crystal will fracture. But if you take a piece of glass and whack it with a hammer, you get random shapes because there's random arrangements. Okay, so a couple of amorphous solids still exhibit some fluid characteristics, and we call them supercooled fluids. An example of that is glass. Glass is technically still a liquid even though it's in the window. Because if you let a window sit there for hundreds of years, it will sag and pool at the bottom. And an old window is thicker at the bottom, thinner at the top, and it may even duck down and start to leave the frame on the top as the glass sags over time and starts to puddle on the bottom. So it still is a solid, but it behaves like a really cold fluid. And some amorphous solids we call supercooled fluids, glass as an example. Yep. So crystals. Some crystals are valuable. This is amethyst, and this is quartz. And some crystals, you know, they've been used as monetary values by people, and we put them on rings because they look neat. Some crystals you eat. Nobody's going to be really impressed if you give somebody a engagement ring made out of salt, right? But crystalline structures have these regular repeatable patterns. Amorphic solids like chocolate or glass, when you look at them and their molecular structure, there's no structure to it. It's just random molecules piled up next to each other. Okay, and again, when you break an amorphic solid, you get random patterns because there's no structure to it. So the stress goes randomly through the material. This is a picture of an old window, and you can see that it's starting to sag out of the top of the frame. And that is an example of why glass is a super cool thing. Okay? Crystal shapes are varied and depend on the number of atoms involved and their charges. So there's lots of different crystalline shapes, and if you look at pages 282 and 283 in your book, you will find many, 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 many of them. I'm just going to give you 3. You don't need to write them all down in your notes. You have a textbook. But these crystals will keep that same shape as the crystal grows. As more and more molecules of that substance are laid down, the crystal will keep the same shape as it grows. So a cubic crystal will be cubic no matter how big it is. So a salt crystal is a cubic crystal. If you were to take salt and look at it under a microscope, it would look like a bunch of dye, right? A bunch of cubes. And then if you find salt growing in a salt field, the crystals are cubic, and they still look cubic, even though they're huge and are going to be broken down by Morton and, you know, put into a shaker for you to use. Tetragonal, I think that's how you say that. Looks that same way, whether it's small or big. And rhombohedral is another one. So these are just 3. There are many. You don't need to know the names of all the crystalline shapes. Just know that they are regular, repeatable structures that the crystal will have no matter how big or small it is. Let me show you some pictures. So this is a cubic crystal. Doesn't that look bizarre? Here's a rock. This is amorphic. There's no structure to this. But an ore of the rock is crystalline. And the ore started to crystallize. And as water laid more and more and more of that substance down, these cubes grew naturally. And you can find a rock in a mine where most of it is amorphic, but then there's these things coming out, and you look, it looks like an artist took some gold like cubes and stuck them into the rock and glued it there, and it took work to chisel it in there. No, that grows naturally. And you look at that and you're like, wow, God likes squares. Okay. And this square thing will grow as a square, no matter how big it gets in nature. Kind of weird looking.
Why does it grow though?
Because the mineral will be dissolved in liquid somewhere, and then as the mineral is deposited by water moving past some other rock and depositing the mineral here, the mineral will arrange itself in this cubic form as more and more of it is laid down.
Oh, so the rock and the crystalline structure isn't the same. Isn't made of the same.
No, this would have something else, and then somehow this crystalline structure started to be deposited, and it grows into this cubic structure as it deposits.
And the crystalline comes from the water dripping, from the minerals in the water dripping onto the rock.
Yep.
So
Yep. So this is a cubal. Obviously, this is a tetragonal, where it starts to look cubic, but then the end is pointy. And as it grows, it'll grow flat out this way and pointy out this way. And so these crystals will keep their same shape as they grow. This is another cubic crystal. Sorry, this is a rhombohedral. This one has 90-degree corners, and this is a rhombus. And so similar, but this is a rhombus. So these are just examples of crystals that grow into this shape, and as they get bigger, they grow that way. I think we're almost done here. Polymorphous solids can form from more than one kind of crystal. So this one, carbon is an example of that. Carbon likes to be a crystal, but depending on the conditions when the carbon starts to crystallize, it will form a couple of different crystalline structures. The graphite in your pencil, if you are using a pencil right now instead of a pen, the graphite is carbon, and graphite is one crystalline structure of carbon. A diamond is another crystalline structure of carbon, and it's still all carbon, it's just how the carbon molecules arrange themselves. So your pencil is made of the same stuff that your earring or ring may be if you have a diamond earring or a diamond ring. And it's just the arrangement of the carbon atoms that make it graphite or make it diamond. There's another form of carbon called a buckyball, where the carbon arranges itself into a sphere. And that is something that only happens in very weird conditions, mostly because a chemist makes it happen in a lab. But it's still pure carbon, it's just carbon spheres instead of carbon sheets or carbon tetrahedrals. Okay? So that's an example of a polymorphous solid. There's more than one crystalline structure that is possible, and it just depends on the conditions that are present when the crystal is forming as to what kind of crystal it would be. Okay, last thing about crystals is lattice energy. And here we're talking about how much energy is present in the crystal. What energy does that crystal represent? And you measure lattice energy, but by looking at the thermal energy present in a gaseous particle of this substance, and then when the gaseous particle sticks to another gaseous particle and begins to crystallize, how much energy is released when that happens is what we call the lattice energy. How much energy, what's the energy difference between the gaseous state and the solid state of this material? So the lattice energy is the energy released when gaseous particles form crystals. It's also how much energy you need to break the crystal apart, same quantity of energy. So if we were all gaseous particles of salt, we're all salt vapor, right? And salt vapor, some of them start to stick to each other and crystallize. They release energy when they do that. That's an exothermic process. And then as those clumps start to stick to other clumps, the thing would fall, and then we'd have a salt crystal starting to grow, right? And eventually you'd have a salt crystal instead of salt gas. And that would have released a lot of heat because there's more energy involved in the salt molecules bouncing around as vapor than there is in the salt molecules sitting next to each other and vibrating. Then the difference in those energies is the lattice energy. It's the same amount of energy it would take if you were to take a salt crystal and vaporize it. You would have to add all that energy back in for it to turn back into a gas. Okay? So lattice energy is what's the energy difference between the gaseous state and the solid state. Phase changes. You've been talking about this since, well, my daughter talked about it last year, so second grade. Melting and freezing is something that is elementary knowledge, right? But now we can give it a little bit more detail. Before it was just, you take a solid, you get it hot, it turns into a liquid. You take a liquid, you get it hotter, it turns into a gas. That's second grade, right? And as you've grown up in science classes, you've done that a bunch of times. How many times have you done a lab where you're melting ice or boiling water? It's all the time, right? But now you get to know why. Because there is this intermolecular force that is constant. The intermolecular force is always there. The question is the intermolecular force stronger or weaker than the kinetic energy that's present? Okay? So let's say that, I don't know how long Alec and Abraham have been friends, but let's just say that they've been friends since 4th grade. I'm just going to make that up. Okay? I'm creating some history for you guys. Alec and Abraham have been friends since 4th grade. And their friendship is always there. And their friendship has been as strong today as it has been in 4th grade, right? Now, they both have military families. So there's travel involved in their lives. And the kinetic energy, we're going to say, is the travel caused by being in a military family. And so right now, the travel force between them is very small. So they can be friends and sit next together in class. And they're solid. They're solid, right? But in 2 years, one of them may get orders from their dad may get orders to go somewhere, to leave, to go somewhere else. Their friendship is still there. The intermolecular force is still present, but now the travel force has gotten stronger. And so now they're broken apart. And one of them goes to Poughkeepsie, and one of them goes to Okinawa, right? But they're still friends. The intermolecular force is still there, but now they're a gas. Because they're far apart from each other, the kinetic force has gotten to be stronger than the intermolecular force. So melting or freezing is the point at which the kinetic energy wins or loses the fight over the intermolecular force. The intermolecular force does not go away, but it may not be strong enough anymore to keep the two particles close together. Okay? So that's melting or freezing. And then in this model of is the molecular force stronger or weaker than kinetic energy, liquid is now seen as a transitional state. Because if the kinetic energy is weak versus the intermolecular force, then they're stuck together and it's a solid. If the kinetic energy is way stronger than the intermolecular force, then they're broken apart and they're a gas. And now the point where they're liquid, where they're like rolling over each other, right? They're still in contact, they're not a gas, but they're not just doing this. Then that's a liquid, where the particles can slide past each other, but they're still in contact. And we can see that as kind of an in-between state. It's not as firm as a solid, it's not as floaty as a liquid, it's in between. A liquid is a transitional state, where the intermolecular forces are strong enough to keep the particles close, but not to keep them still. Okay? There's been a ton of information here. What questions do you guys have? Intermolecular forces, the 3 kinds of them, or just what they are? The dipole, the hydrogen, and the London, right? Yeah, so the reason things stick together is because the molecules are attracted to each other. And the molecules are attracted to each other for 3 possible reasons. 1, because they have positive and negative portions that are attracted. That's the dipole-dipole. The strongest version of a dipole-dipole is the hydrogen bond, where a hydrogen is attached to an oxygen, and the hydrogen loses its electrons almost entirely. So there's a very strong proton sitting out there, and a very strong negative force, and they like to orient so that they're attracted to each other. And then the London forces is where the molecule as a whole does not have a dipole moment. There is no polarity to the molecule as a whole. But because electrons are traveling, there may be a split second in time where the electrons are more on one side than another. So that's more negative, and the other side's more positive. So London forces are just temporary. I'm attracted to you, no, just kidding about it. Okay. Any other questions?